Hello, my dear students, and welcome back. I know. Exams are just around the corner, and this chapter, hydrocarbons, it can feel a bit scary, right? But please, don't you worry at all. In the next few minutes, we're going to break it down and make it so simple and clear. You'll feel completely ready by the end. So let's do this together.
Look, I get it. You hear alkanes, alkenes, alkynes, all those reactions, and your head starts spinning. It just looks so complicated, doesn't it? But trust me, Beta, it's really not. We are going to break it all down, step by step, just you and me. And by the time we're done, you're going to feel so much more confident. That's a pocket promise.
Okay, so here's our game plan. It's a simple 5-step master plan. First, we'll meet the hydrocarbon family. Then, we'll see how naming is actually a fun game. After that, we'll jump into the really important chemical reactions. We'll also touch on a couple of special topics, conformations and benzene. And to finish it all off, we'll tackle some top exam questions. Think of it as our perfect roadmap to absolutely ace this chapter.
All right, Section 1. Let's meet the hydrocarbon family. First things first, let's get to know the basics. Think of it like this. We're getting to know the main characters of our story. So, who are these hydrocarbons anyway? Come on, let's find out.
You see, it's actually quite simple when you look at it this way. Hydrocarbons basically come in two main types. You've got your saturated and your unsaturated. Now, the saturated ones, those are the alkanes. They only have single carbon-carbon bonds. Think of them as completely full and satisfied, But the unsaturated ones, the alkenes and alkynes, they are hungry. They're hungry for more bonds, which is why they have double or even triple bonds. And you can see it right there in their general formulas. They have fewer hydrogen atoms because of those extra bonds.
And if that helps, let's make it even simpler. Just imagine they're all siblings in one big family. The alkanes, the saturated ones, they're like the calm, stable sibling. All single bonds, totally happy, doesn't really want to react with anyone. That's why they used to be called paraffins, which literally means little affinity. But then you have the alkenes and alkynes. Oh boy, they are the super energetic, super reactive siblings. They've got those extra pi electrons just sitting there, ready for action, waiting to start a chemical reaction.
Okay, moving on to Section 2. Naming is a fun game. And listen to me, Beta, this part is super important for your exam. I know, mastering IUPAC nomenclature sounds really tough, but I promise you, it's not. It's just like a game, and once you know the rules, it becomes so easy. So let's learn these rules together, shall we?
It really just comes down to these 4 simple steps, okay? Step 1, find the longest continuous carbon chain. That's your parent chain. Step 2, you got to number the carbons, and the trick is to start from the end that gives any branches or substituents the lowest possible number. Step 3, name those branches, the alkyl groups, and write down their position number. And finally, step 4, just arrange all those substituent names alphabetically and write out the full name. See? Easy peasy.
Okay, so let's practice. Time to put those rules to the test. What's the IUPAC name for this compound? Now, don't let those brackets scare you off. The first thing you should always do is draw it out. So I want you to hit pause right now, grab a pen and paper, and try naming this yourself using our 4 steps. Come on, go for it. Give it a real try. All right, you're back. So how did you do? Did you get it? The correct answer is 2,2,4,4-tetramethylpentane. See, it wasn't so bad. If you draw it out, you'll find the longest chain has 5 carbons, which makes the parent pentane. And then you have 4 methyl groups as branches. 2 of them are on carbon number 2, and the other 2 are on carbon number 4. Simple, Henna?
Next up, another concept that is so important, isomerism. Okay, what is it? Well, think of isomers like they are twins. They have the exact same molecular formula, the same number of atoms, but their structures are completely different. And just like twins can have different personalities, these isomers have different properties. Because their structures are different, things like their boiling point will be totally different.
And here's a perfect example for you. Look at these two. On the left, you have N-butane, which is just a straight chain. And on the right, you have isobutane, which is branched. Now look, both of them have the exact same formula, C4H10. But because their structures are different, their boiling points are different. The branched one is more compact, more spherical, so its boiling point is lower. Isn't that amazing? Just by changing the arrangement, you change everything.
All right, Section 3, important chemical reactions. Okay, let's gear up for what is probably the most action-packed part of this chapter.
Now, we're not going to go through every single reaction in the book. No way. We're only going to focus on the reactions you absolutely must know, the superstars that show up in your exam again and again. You ready for this?
And first up, we have a real celebrity in the world of addition reactions, Markovnikov's rule. Now, the name sounds all complicated and serious, I know, but the idea behind it is actually very simple. It says that when you add something like HBr across a double bond, the negative part, in this case the Br-, is very picky. It goes to a very specific carbon atom. The big question is, which one?
So, what's the logic here? Why does this rule even work? Well, it's all about one word: stability. See, the reaction happens in steps. First, the H+ from the HBr attacks the double bond, creating a temporary positive charge on a carbon. We call this a carbocation. Now, the reaction can create two possible carbocations, but one of them, the secondary one you see with the green tick, is way more stable than the other. And chemistry is lazy. It always chooses the easiest, most stable path. So the Br- will then attack that more stable carbocation. But here's a super simple trick to remember it, okay? Just think, the rich get richer. The carbon atom that already has more hydrogen atoms gets the new hydrogen atom. Simple.
But wait, just when you thought you had it all figured out, there's a twist. If you do the exact same reaction but add a little bit of peroxide, boom, the rule flips completely. This is called the Anti-Markovnikov addition, or the Kharash effect. Now, the Br goes to the carbon that has more hydrogens. But please remember this. This special effect only, and I mean only, happens with HBr and only when peroxide is present. For everything else, Markovnikov's rule is the boss.
You are doing a great job, really. Now let's jump into Section 4, Special Topics. We're just going to quickly cover two little topics here that often pop up as short answer questions. So pay close attention for the next couple of minutes because these are some of the easiest marks you can score in your exam.
First, let's talk about the different shapes, or conformations, of ethane. Because there's free rotation around that carbon-carbon single bond, the molecule can twist, so you get different arrangements. The one on the left is called the staggered conformation. See how all the hydrogens have their own space? They're far apart. It's relaxed, it's stable. You know, Eclipsed. But the one on the right is the eclipsed conformation. Here, the hydrogens are right behind each other. It's crowded, there's repulsion, it's unstable. So naturally, which form do you think the molecule prefers? The stable, staggered one? Of course.
And now, let's talk about the undisputed king of aromatic hydrocarbons, benzene. Its formula is C6H6. A brilliant chemist, August Kekule, came up with this amazing ring structure with 3 double bonds. But here's the magic of benzene. Even with all those double bonds, it is unusually, incredibly stable. And it's so important. It's the starting point for making so many things we use every day, like dyes and even medicines.
Okay, here we are, the final section, the rapid-fire round. It's time to put everything we've learned together and tackle a top exam question. Think of this as the final boss battle. Solving this will really test your understanding and give your confidence a huge boost. So, are you ready for the challenge?
Here it is. This is a classic, a very popular question they love to ask. How will you convert ethanoic acid into benzene? Whoa. At first glance, it looks really tough, right? But it's not. It's just a puzzle. All we have to do is connect the different reactions that you already know. Let's solve this puzzle together, step by step.
Okay, so here's the path from ethanoic acid all the way to benzene. Let's trace the steps. Step 1. We take our ethanoic acid and react it with soda-lime to chop off that CO2 group. That's called decarboxylation, and it gives us methane. Now we have methane. Step 2. React that with chlorine in sunlight to get chloromethane. Good. Step 3. Now for a clever trick called the Wurtz reaction. We use sodium to stick 2 chloromethane molecules together, and that gives us ethane. See how we doubled the carbons? From there, it's a couple of standard steps to get from ethane to ethene, and then to ethine. And now, for the final magic trick, you take that ethene, you pass it through a red-hot iron tube at 873 Kelvin, and poof, you get benzene. And remember this number, 3. That's the key to the final step. In that red-hot iron tube, exactly 3 molecules of ethene come together. They kind of hold hands in a circle, and they polymerize to form one single, beautiful, stable molecule of benzene. How cool is that?
And that is it. We've done it. We've gone through all the major highlights of the entire hydrocarbons chapter. My dear students, please believe me when I say this. You have absolutely got this. Just go back, revise these key concepts, maybe practice naming a few more compounds from your textbook, and you are going to do wonderfully in your exam. I have complete and total faith in you.
Now, before you go, do me a favor, let me know in the comments below what's one other reaction or topic from this chapter that you still find a little tricky. I'll read through them and try to help as many of you as I can. Keep up the amazing work, keep studying hard, and I will see you in the next one. All the very, very best.